So this is the start of Unit 2. We're going to be talking about traffic accidents, and if you want to follow along in Worksheet 2-1, you can write down the equations there, and you don't have to worry about doing that later on. Nothing you have to write down for these first 3 slides. It's just a review or maybe an introduction of Newton's 3 laws. So the first law is that a body in motion stays in motion unless some other force acts on it. That's why you should wear a seatbelt. So if we see a head-on collision between this car and this brick wall here, head-on collision, if this man here is wearing his seatbelt, he's going to in essence become part of the car, so that when the car is stopped by the brick wall, he's going to be stopped by the brick wall as well. If he's not wearing his seatbelt, then he's not part of the car, and he will keep moving forward and be thrown from the car. So the net force would be the force of the seatbelt on this man. If he's not wearing a seatbelt, then he will stay in motion because there's no net force that acts on him. Newton's second law is an equation. It's the force equation. So I guess you could write this one down now. Force equals mass times acceleration. If you want to use those as abbreviations, F equals m times a, mass times acceleration. As long as you know what those letters mean as an abbreviation, you can just use that. So the question here is, if you run out of gas, how much force is needed to push your car? The force is what you're trying to find here. Here's the mass of the car, and here's the acceleration. So you just multiply the mass times the acceleration, and you get the force that you need to push your car. Newton's third law is, for every action, there's an equal and opposite reaction. So here we have the rocket fuel. Combustion of the rocket fuel is the action. The reaction is that propels the rocket over to the right. Same thing here, but just vertical instead of horizontal. So rocket fuel combustion comes out this way. The reactive force is the rocket moves up off the ground. When accidents are being analyzed, police use Newton's laws and physics equations during that analysis. The kinematics equations are combinations of equations. They're used to calculate braking distance, acceleration, and change in velocity. So these are the 2 big equations that we're going to be using, and you need to learn how to use. And then I show you what the abbreviations are for below. So the first one, you have distance. If you're calculating stopping distance, you have initial velocity and final velocity. You add those together. Initial velocity is the start, obviously, and final is the end velocity. Now, for the most part, in an auto accident, your final velocity is going to be 0 because the autos come to a stop, and the initial velocity is going to be cars are moving along at a certain speed. So that's maybe different from what you've seen in other classes. Your final velocity is more often than not going to be 0. Probably always in this class. And then T stands for time. So final velocity, more often than not, is going to equal 0. And this is going to be meters per second. Same thing goes for the next kinematics equation as well. with the final velocity. Again, calculating the final velocity, you're going to set that equal to 0. You want to figure out how fast that car was going. The initial velocity, you'd solve for that, and then you add that to 2 times the acceleration times the distance. So how do you tell the difference between how do you tell which one of these equations to use? Basically, the difference is right here. So if there's time, okay, now you can't see that, sorry. If there's time involved in the equation, then you use this kinematics equation. If there's acceleration involved, then you're going to use this kinematics equation. The kinematics equations are combinations of a lot of these equations that are following. These are simpler equations here. Cars have both velocity and acceleration. So the velocity equation is distance divided by time. These conversions are really important. 1 mile per hour equals 1.47 feet per second. If you're calculating stopping distance, you want to convert from miles per hour because your stopping distance in miles is going to be really, really small number. And then if you're converting from 1 meter per second, which is what we use in our physics equations, and you want to calculate speed in the units that we know, miles per hour, you're gonna use this conversion as well. And then we have acceleration is velocity divided by time. This is Newton's second law, just to review. You have force equals mass times acceleration. Really important, the unit of this is a Newton, capital N. So if you have mass times acceleration, or you're doing the force equation, you're going to just take all the other units out of your answer and combine them together to give a Newton. Friction force, coefficient of friction. The friction is between the tires and the road, the brakes, the suspension system, and then road conditions. You're not going to really be doing any calculations necessarily with this, but you need to keep in mind where the coefficient of friction is the highest and where the coefficient of friction is the lowest, especially between the tires and the road. Dry tires and dry pavement and good tires with good tread is a high coefficient of friction. So high coefficient of friction is new tires, dry road conditions. A low coefficient of friction is going to be old tires where their tread is wearing off, and some sort of precipitation on the road. Snow, ice, rain. So a low coefficient of friction is old tires and a wet road with some sort of, like I said, with some sort of precipitation. We're almost there. The momentum equation is used to try and figure out maybe starting speed of an object. So the momentum, and I don't know why the momentum is abbreviated by letter P, but it is, mass times velocity. So mass times velocity is what we're using here. And your unit is the units of mass and velocity, kilogram times meter per second. Last equation. Kinetic energy, the energy of motion. How much energy is behind a car before it crashes? How much energy is put into that collision? So this is kinetic energy. It's 1/2 the mass times the velocity squared. So if you look at that, you're squaring the velocity. So if you double the speed, like you're going 2 miles an hour, that factor is going to be 4. If you go 4 miles an hour, that factor is going to be 16 because you're squaring it every time. So the speed, the velocity of the car is very important. It plays a huge role in the energy that's involved in a collision. The unit here is a joule, capital J. So just like when we were using the force equation and we just put newtons and N as the unit, here with kinetic energy, the unit is going to be joule, capital J.